Hi everyone, I am Deepika and my batchmates are Saukya and Aditya. Here we worked on a project named Approximate Ternary Adders under the guidance of Dr. V. Srihari sir. Our project is about reducing the hardware complexity and increasing the efficiency as well as decreasing the power delay product and the power consumption. Using the approximation technique, we can decrease the hardware complexity and using the ternary logic in the adders, the power delay product and the power consumption decreases. So we have used the ternary logic, but not the binary logic. Now let's get into the comparison between the binary and the ternary logic. The binary logic has two logics, that is 0 and 1, but in the ternary logic we have three states, that is 0, 1, 2. Here we have the intermediate state, so we can use the intermediate voltage values. These are the voltage levels for the respective logic values, that is 0 represents the ground level, but 1 represents the half of the source voltage, and the 2 represents the voltage level, sorry, the source level. um, and this is the representation of binary from the decimal. Here in binary we have 8421, but in the ternary we have 3 and 1. uh, let's get into the inverters now. The binary inverter has only one standard inverter, that is it converts the 0 to 1 and vice versa, that is high to low and low to high. But in ternary we have positive three inverters, that is PTI, STI and NTI, where the stands for positive ternary inverters, negative ternary inverters and standard ternary inverters. Here we can replace the ternaries with the respective of the usages. Like we can convert the 0 1 2 to 2 0 0 in NTI, in and 2 1 0 to STI, and 2 2 0 in PTI. And this is the AND gate of binary. In binary AND gate, we consider the minimum of both the inputs. That is here, the minimum is 0, so the output is 0, and it also applies to the same in the ternary, that is the minimum of both the inputs is the output. And an OR gate, it is reverse of AND gate, that is the maximum of the out inputs are considered as the output. So come on, let's take this example. Here 0 1, the 1 is the maximum in both of the inputs, so 1 is the output. Same, it also applies in the ternary logic. And this is the binaries OR gate. Here for 0 0 we get 0, and this is, we don't have any uh, XOR gate and ternary logic. Uh, these are the gates. These are the remaining gates. We have considered six gates, that is AND, OR, NOR, NAND, and XOR gates. And let's get into the half adder. This is the binary half adder, where we have only two inputs and two outputs, that is carry and sum. Here we have taken this carry and sum, unlike the regular truth table that we have sum and carry. But here we are considering this has uh, MSB, and this has the LSB. This is the ternary half adder. In This is the full adder of ternary. And let's get into the 4-bit addition in binary. Here if we take 4 bits, 1 1 1, and here 1 1 1, and the second B bit. So if 1 plus 1 is 0. uh, 1 plus 1 is 1 0, so we take 1 in carry and 0 as sum. So again we add and we get here 1 as the carry and the other remaining is a sum. And this is the ternary addition. This is the same as the binary addition. There's nothing difference in both the additions, but the 2 is in between, that's it. And we have classified the adders into three types, that is decoder based, mux based, and transistor based. The decoder based has mm, five types, that is ternary logic gates, and ternary and binary logic gates using AOI, NAND gate with dual VDD, and a ternary NAND gate with dual VDD. Mux based has four types, that is 3 is to 1 mux and 3 is to 1 mux and unary operators, and 3 is to 1 mux and 2 is to 1 mux and 2 is to 1 mux. The transistor based has two types, pass transistors and transistors and encoders. This classification is based on our base papers. We have considered uh, 10 11 base papers actually. So based on those base papers, we have classified our adders into three types. So these are the base papers for project from so this is the first paper we have considered from AP Dande and VT in goal. This is the decoder, A bit decoder and B bit decoder. Here we are taking uh, the ternary logic gates, and this is the block diagram for decoder. And here we get the sum and here we get the carry. Here we use the ternary logic gates and the ternary inverter. This is about the first design, and this is the second one. We have used only the decoder and the binary gates, and including the ternary inverters in the sum and also the ternary inverter in the carry. This is our third design, that is using the 3 is to 1 mux. This is also another design that is 2 is to 1, based on the 2 is to 1 mux. Now we will take an example, that is we will take the A as 0 2 0 and the B1 as 2 2 0 0. Here after the calculation, after using the logic gates, we get here as 0 0 0, and here also 0 0 0 and 0 0 2. After this we get 0 here, 0 here, and 0 here. This 0 is converted into 0 by using so therefore we get sum as 0 and carry as 1. This is the third adder we have considered from SK Saho and G Akhilesh paper. uh, we have used the decoder here and the binary logic gates and the ternary inverters. This is the fourth design. This proposed decoder is proposed by the authors itself, and they have used the dual voltages here, and they also proposed an the ternary NAND here. The fifth design is based on the binary gates and the ternary gates and all, as well as the dual voltages. And this is the sixth design. This is the mux based design. That This is the 3:1 mux base design. And this is the seventh design. This is the eighth design. From the eighth base paper, we have considered. Here we have used the past transistors. We will get into detail with this. That we have three types of stages here. This is a successor stage. This is a predecessor stage, and this is the same stage as well. This is the main design. Uh, our project is based on this design actually. Here we have the x1 generator block and x2 generator block. This is the sum encoder block. This is from uh, as Abhay S. Vidyardhan and Sanjay S. Vidyardhan. This is the 11th design we have considered, that is an half adder sum and generator, and also the transistors. So now let's get into the approximation details very briefly. So our project is about is introducing an approximation into the design. So adding a small amount of approximation may reduces the hardware requirements. That is, we can reduce the space of the adder, so that it doesn't take much more space. So this increases the efficiency and also reduces the error percentage. So this is the accurate adder. Here AN, AP, BN, BP are the inversions of NTIs and PTI, where AN represents the inversion of standard uh, of it, sorry AN AN indicates the inversion of the uh, NTI values of A, and AP uh, indicates the inversions of these values. So 0 is converted in NTI as 2. The inversion of 2 is 0. So here AN is 0. We have used this AN, AP, BN, BP because to avoid the 1 in the whole table. So we don't see here 1 at all, only zeros and twos. So we need to avoid 1, so we have taken NTIs and PTIs. And these are the K maps for the accurate adders. This is for the x1 generator block. This is the x1 and this is the x2. So this is the K map of x1 and this is the K map of x2. And coming to the accurate adder circuit, this is the diagram for it. Now the error analysis of both the x1 and x2. Here the error should be below 5% in both x1 and x2. So we need to ensure that it is below 5%, or else our design cannot be validated. So by adding the error directly into the K map, we have analyzed the error. So we have included 2 here instead of 0. So after that we have received an equation here, and instead of 0 here we have introduced 2. That is an error. We have only introduced 2's in one place, and Again, here we have introduced into two error in two places, and this is another case. Here we have introduced in the second position, instead of 0 we have introduced 2. This is also another case where we have inserted two errors. uh, we have taken the first case as the first two. So we have considered the seven cases. For the first case we have considered the equations without errors, and after that we have taken the probability of all the cases, and we have mixed matched it, and we have taken the uh, true tables for it. After the came getting the equations, we have drawn the true table for that, and we have got the errors here exactly. The Based on this table we have drawn the circuits for case 1, and considering the case 1 we have got uh, the error analysis for all cases. These just fall under 0 to 1%. uh, we have got 6730 cases. So multiplying 6730, 6730, this is the total number of cases. This So most of the cases most of the error fall under 0 to 1%. After that, case 2, for case 2, this is the truth table, and this is the circuit, and this also comes below 5%. Most of the cases fall under the error comes under 0 to 1% and 1 to 5%. And this is case 3. This is the truth table, and this is the circuit, and the most of the cases error is under 1%. So this is also considerable. And this is case 4. This is case 5. This is case 6. This is all the similar manner. We have just considered changed the equations, and got these two tables and the uh, circuits, and this is the analysis. Now after these we are going into the 8-bit addition block diagram, where this is the first 0th bit, first bit, second bit, third bit, and so on. Here the carry goes into the full adder of first bit, and the carry goes into the next late the same the carries to the next to the next full adder. This is the accurate 8-bit addition. Here for approximation, the first 4 bits are taken approximate, but the other 4 bits are taken as accurate. Here this is the calculation of error percentage. Here the error percentage is calculated as accurate minus approximate by accurate into 100, where this says the error into 100 says the percentage of the error. So this is the accurate for considering the case 1. This is the accurate sum, and this is the approximate sum. Applying this formula, accurate minus approximate by accurate, we have got the error percentage as 1.6 1.06%. Considering case 3, we have got 0.9%, and case 2 0.2%, sorry, 1.2%. and for case 4 0.29%, and for case 5 0.3%, and same for the case 6. And for seventh case, we have got the error percentage as 1.07. The error analysis For the error analysis, we have considered uh, uh, MRED and MED and NMED parameters, where MRED is stands for mean relative error distance, that is uh, RED by relative error distance by the total number of cases. Here, relative error distance stands uh, logic is accurate output minus approximate output by accurate output. If we have divided by the total case, we get the mean relative error distance, and these are the remaining parameters, that is mean error distance, that is n by total number of cases, where n is sum of all differences, and error rate. Error rate is the number of wrong outputs by total number of the test cases. It is same like as probability of getting the wrong outputs. And normalized mean error distance, where it is the mean error distance is divided by the number of total input values. By considering all these parameters, we have taken the error analysis in this table. For case 1, these are the values we have got in all the parameters. This is the total table of error analysis, and after this we have after introducing the error into the circuit, we have got the resultant transistor count in this. All The transistor count has been reduced to 34 is minimum and 40 is the maximum. So you can see the difference here it is 130, but here we have reduced to 34, 30, 40, 40, and 22. So after introducing an error which is less than 1% or 5%, we have got the transistors count like this. So this transistor count decreasing indicates the decrease of hardware complexity. So this is the final proposed approximate adder of our project. And after we have given an application for this adder. We have given this to the image processing application. So here we have got PSNR and SSMI as these values. Uh, this is for These are the existing. The first three designs are the existing designs, where this is our proposed design. You can this is the same, and we have the image processing applications are like sharpening, so you can see the different images. This is the input image, this is the accurate designs output, and this is by the uh, existing designs, and this is by the proposed design. This is the output of our proposed design. So after this error analysis, this has been reduced to uh, uh, the picture is enhanced by 67%. The we have The conclusion is that our design has been into the less has the less transistor count and less hardware complexity, where it has more efficiency than the existing designs. Thank you.